The next force we're going to talk about is the spring force, which is referred to as Hooke's law. Now, a bit of trivia. I guess this is for all those people who've taken biology, which hopefully is everybody who's watching this video. What else is Robert Hooke famous for? It's a biology thing. He's a naturalist, much in the same fashion as Galileo, much in the same fashion as Newton, is that he spends his life exploring nature. Well, one thing that Hooke discovers is he discovers the plant cell wall. He's the one that dissects cork. And notice that there's small sections of cell wall there. So that's what Robert Hooke is also famous for, is discovering the cell wall. This is kind of a little bit of interesting bit of trivia. Like you have Descartes being a philosopher. You have Newton, who actually is an alchemist, and now you have Robert Hooke, who's probably more famous in biology than he is in physics for his discovery of the cell wall, not the property of a spring. Okay, so this is Hooke's law. Hooke's law says that if you stretch a spring, you experience a force on that spring. The most important thing about Hooke's law, though, the critical thing about it, is if you stretch that spring. So if you pull the spring down, so here's my diagram. Let me see, move over. Let me get over here. Maybe if I grab a stick. If I stretch the spring over here, so this first one is a non-stretched spring. If I stretch it by hanging something on it, so it pulls the spring down, down, then I experience a stretch. I experience a displacement. I experience a change in my position. So in a sense, I can change this. I can say this instead. So this is the stretch in which the spring is experiencing. Let's be careful with that arrow. That it stretches downwards by that much. Okay? So you hang that mass and it stretches downwards. Well, Hooke says that the response of the spring responds to that by how much you stretch it. So it'll respond with whatever force depending on how much you stretch it. But that response, that force that it responds with, depends on two things. It depends on what's known as a spring constant. This K constant, it keeps coming back and into our vocabulary. You see that K and you should think constant by now. The spring constant, which is a geometry of the spring. It's how tightly it's wound. It's how the ends look. Will it spin? Will it not spin? A whole bunch of things. The tensile strength of the material. There's a whole bunch of things that go into what this spring constant is. Okay, but it's just a constant for each spring. Each spring has its own constant. So that force that it responds with is equal to the spring constant times the amount of stretch that it experiences. So if you grab a spring and you stretch it, the more you stretch it, the more force you experience. Up until a point. There's a point in which this collapses. You've stretched the spring so much that it won't return back to its original position. At that point, Hooke's law doesn't hold true, and your spring is nothing more than junk. It's not a spring. It's a bent piece of wire at that point. Okay? So that's Hooke's law. The really cool thing is that if I stretch it this way, there's a negative sign in front of here that's saying if I stretch it down, that the force I experience is in the opposite direction. Okay? The spring force is also referred to as a restoring force. It's trying to restore that object to its original position. Okay, so if I stretch it in this direction, then the force is in the opposite direction. Now, if I were to look back at my kinematics, what kind of motion had a acceleration, which we know is related to force? Which of my motions had an acceleration that was opposite of my position? So if I had a position down, my acceleration was in the opposite direction. What kind of motion created that? Well, or what kind of motion had that phenomenon? I shouldn't say created that. It should have had that phenomenon. Well, the answer to that is simple harmonic. This is a simple harmonic system. My force is responding to the opposite direction to the stretch. Stretch is down, force is up. If I compress the spring, then my distance is in this direction, and then my force is pushing down. So we experience simple harmonic motion in this case. unless we simply hang that object and just let it sit at the bottom so that there is no acceleration. But I just wanted to point out that this is a restoring force. We've experienced a force in the opposite direction of the stretch, and that's what creates simple harmonic motion. A little bit of a glitch there, I guess. Okay? Hooke's law. Spring force. The response to the stretch of a spring is equal to, well, the response being the force, is equal to the constant of the spring, this property that the spring has, times the amount of stretch. And that force is in the opposite direction of the stretch. Okay? That's Hooke's law. And when I'm using the word stretch, I should say really quickly, I'm actually referring to the words that are above me. Stretch can either, you can think of it as a displacement as it's moving from one point to another, or if you think as the original position here, excuse me, as the origin, then displacement and position are about equivalent to each other. Okay? So spring force, Hooke's law.